All right, today we're tackling a super famous coding puzzle from NeetCode. It's called Subtree of Another Tree. Now, I know, whenever you hear terms like binary trees or algorithms, it kind of sounds intimidating, right? But seriously, forget the jargon for a second. We're not just looking at code today, we're looking at a puzzle. And by the end of this explainer, you're going to see exactly how elegantly we can solve this using some really straightforward logic. So imagine this scenario for a minute. You're on a search and rescue mission, but you're not looking for a person. Actually, you're looking for a very specific, uniquely shaped branch hidden somewhere inside a massive, sprawling oak tree. You've got a photograph of the exact branch you need to find, but here's the catch. This giant oak tree has hundreds of branches that look, somewhat similar, and you need an exact match. So how do you systematically search this giant tree without getting completely lost or, worse, checking the exact same spots twice? Well, that is exactly the challenge our algorithm faces today. Section 1. The tree within a tree. Now, what's really cool is how this breaks down our two main characters. On one side, we have our root. This is that massive oak tree, the main data structure we need to search through. On the flip side, we have our subroot. Think of this as the photograph in your hand, right? The specific smaller tree you're trying to locate. But listen, here is the absolute critical role. Finding a match isn't just about spotting a familiar leaf or a single number. The root's subtree and the subroot, they must be absolutely identical. I mean, a perfect match in both their overall physical structure and the exact value stored inside every single node. If literally even one leaf is out of place, no deal. It's not a match. Okay, moving on to section 2, diving deep, the DFS analogy. To keep from getting totally overwhelmed by the sheer size of the main tree, let's think like a detective searching a massive mansion. A good detective doesn't just run wildly from the first floor to the third floor, peeking into random rooms, right? No way. They follow a strict protocol. Step 1, they pick a hallway. Step 2, they walk down that hallway, opening doors, going deeper and deeper until they hit an absolute dead end. And then step 3, only when they can't go any further do they backtrack to the last intersection and check the next available path. This brilliantly illustrates the exact logic of our algorithm. We go deep before we go wide. And this detective strategy actually has a formal name in computer science. It's called depth first search, or DFS for short. Our source material actually points this out explicitly in hint 2. Because we need to check every single node in our main tree to see if it's the start of our identical matching subroot, we use DFS to navigate. We travel all the way down the left side of a branch, hit the absolute bottom, and then step back up to check the right side. It just ensures we visit absolutely everything exactly once in a highly organized way. Section 3. The same tree helper. So picture our detective walking down the hallway, navigating the tree using DFS, right? And they step into a room. This row represents a node in our main root tree. Now they need to pull out that photograph, the subroot, and compare. To do this, we use what's called a helper function. Think of it kind of like a high-tech fingerprint scanner. We'll call it SameTree. The crucial thing here is that this scanner checks 3 things all at once. First, do the values of the current nodes match? Second, if we look down the left path of both trees, do they match perfectly? And third, if we look down the right path of both trees, do they match exactly? If all 3 conditions are a go, the scanner flashes green. Boom, we've found our identical subtree. All right, section 4. Putting the pieces together. Let's see how this all builds together. It's actually really beautiful. We have our movement, that's the depth first search. And we have our fingerprint scanner, that's the same tree helper function. The whole algorithm works by recursively zipping down the main tree. At every single node it encounters, it just pauses, pulls out the subroot reference photo, and runs the same tree check. If the check says false, hey, no problem at all. The algorithm just keeps moving down the hallway, continuing its DFS journey to the next node. It repeats this continuous process of moving and scanning, until it either finds a perfect match and returns true, or it searches the entire tree and confidently returns false. It's just incredibly elegant when you view it from this perspective. Section 5. Time and space complexity. Now, before we get into the final math, let's take a quick look at our constraints. The source material highlights a very specific number for this problem, 100. Both our main tree and our target subtree will have a maximum of 100 nodes. Plus, the values inside those nodes, they'll only ever range from -100 to +100. This is actually fantastic news.
It tells us that while we absolutely need an efficient algorithm, we aren't dealing with billions of data points here. It keeps our expectations grounded and lets us know our DFS approach is going to be incredibly fast in practice.
Okay, now for the big O complexity. If you're a beginner, this jargon can definitely look a little scary, but let's just demystify it right now. Look at the time complexity, O of m times n. Let's say n is the number of rooms in our main building and m is the number of rooms in our target subbuilding. In the absolute worst case scenario, like maybe the trees look almost exactly alike but fail at the very last leaf, our detective has to stop at every single room in the main building, n, and scan it against every single room in the subbuilding, m. So we literally just multiply them together, m times n. Simple as that. For space complexity, it's O of m plus n. This is really just the memory our computer needs to keep track of the detective's path back up the hallway, basically the maximum depth of both trees combined. And that brings us to the end of our breakdown. We've taken a complex coding problem and basically turned it into a simple search and rescue mission using depth-first search and a handy fingerprint scanner. But before we wrap up, I want to leave you with this provocative thought. Where else in your everyday, physical life do you subconsciously use a depth-first search strategy? Really think about it. Like, how do you look for your lost car keys? Or how do you navigate a maze? Or even, how do you read a deeply nested thread of comments online? Algorithmic logic isn't just for coding interviews. It's honestly a fundamental part of how we naturally navigate the world. Thank you so much for joining me on this explainer, and I really hope this makes your next encounter with a binary tree a whole lot more fun.